Welcome you to this series of lectures on marine aerodynamics. Today we have the 19th lecture, and today we will talk about vortex motion. Although I have already introduced to you the vorticity vector, which gives us about the flow in the angular directions. Then we have also talked about the vortex and also circulation. So, first I will summarize in brief about what we know, and then go to the details, a little more details about the vortex motion. This will start with the basic definition of vorticity. So, what I understand by vorticity? If I have a velocity vector q bar whose components are u, v, w, these are the velocity of a fluid particle, the components of the velocity of the fluid particle, then what will happen to omega bar, which is nothing but curl of q bar. Curl of q bar will represent the angular velocity of the angular. Curl of q bar will give the velocity in the rotational direction, basically the angular, it is a measure of the angular velocity, and which is also can be written as I j k, then del by del x, del by del y, and del by del z, u by w. And so, what will happen? This is the curl of q bar. It has three components: one is the I component, one is the j component, one is the k component. Then we will see that if this is the vorticity vector, is the vorticity vector. Vorticity vector, and then we have, if omega bar is 0, we all know that we call this as vortex free motion. Or irrotational motion. So, if the flow is, if I consider my flow is two dimensional, then and flow is two dimensional and motion is rotational. This is just what all I have talked about. Then we have omega bar is equal to 0, which gives you omega x is equal to omega y is equal to omega z is 0, and that gives me del w by del y minus del v by del z is 0, then del u by del z minus del w by del z del x is 0, and we have other things, that del u by del y minus del v by del x is 0. So, this is what happens when we have a vortex free motion. For vortex free motion, or when the flow is rotational, we have this. And then we all know that once we know the vorticity vector, then we can always talk about the vortex lines. This is just a kind of review, because I have already talked about some of these things. Vortex line. A vortex line is a curve think of a curve, and need not be a closed curve, or rather let us look at a curve. Is a curve drawn in the fluid. It is such that the tangent at any direction, it is in the direction of the vorticity vector. So, that means this is, if omega bar the vorticity vector and dr bar the tangent at any point we will draw, then the both are parallel. That will give us, so equation of the vortex line will give us omega bar cross dr bar is 0, and once they are 0, that will give us dx by omega x, dy by omega by dz by omega z, and that will give us the equation of the vertex line. Then what I will talk about a vertex tube. Suppose I consider any closed curve. If we draw, consider any closed contour in the fluid, and we draw the vertex lines at each point. Draw the vertex lines at each point, and then of this closed curve. Then the space bounded by these lines, whole space bounded by these lines, is called a vertex tube. And this is called a vertex tube. However, and the fluid that exists inside the vertex tube, within the vertex tube, is called a vertex filament. This is called a vertex filament. Is the fluid that remains inside this tube. It is called a vertex filament. So, I can always say that a vertex tube is nothing but it is the boundary of the vertex filament. Now, if you look at the strength of a vertex tube, strength of a vertex, what is the strength of a vertex? Suppose K be the circulation, let K be the circulation around a closed curve. And sketch the circulation around a closed curve which encloses a vertex tube. Then if C is the boundary of this closed curve, then what will happen to K? K by definition is integral over C q bar dot dr bar, that is what the definition of a circulation. And if q bar dot dr bar, if I apply Green's theorem, that is nothing but over the surface curl of q bar dot n hat into ds. If I put it in the component wise, it will be integral over x L omega x plus m omega y plus n hat. So, dz ds. Now, if I assume that pi a square is the cross sectional area of the vertex tube, area of the vertex tube, then what will happen to K? K will be pi a square into L omega x. Already it is a scalar, so it is okay. Have L omega x plus m omega y plus n omega z, and this is what. So, this has to be, because the circulation around a closed curve. So, this will be a constant. If this is a constant, because then what I say, then I call K the strength of the vertex. I call K the strength of the vertex. This is assuming that A is small. We assume A is small. This is the assumption. Otherwise, it would not. So, then we call K as the strength of the vertex. Once we know the, now let me say another term, what is called a rectilinear vertex, because these terms will be used afterwards every now and then. The liquid which within the cylinder of which the circle is a cross section. Circle is a cross section. The liquid within a cylinder of which circle is a cross section is known as a is said to form a rectilinear or column vertex. So, now what we will do, how to find WZ for a rectilinear WZ, that is basically the compressive velocity potential due to a rectilinear vertex of strength K. Find WZ for a rectilinear vertex of strength K. In fact, these things will clarify many things which earlier we have introduced many of these things, but we have never, things are certain clarity will come once these things are discussed. Now, let us consider a cylindrical vertex tube in the xy plane. Consider a cylindrical vertex tube. And this is first, to let the tube be surrounded by incompressible rotational fluid, and a rotational fluid. And let the motion be 2 dimensional. Assume 2D motion of which u is equal to u x by v is equal to v x y, these are the components of velocity, and w is equal to 0. Then because of this, then we have only thing that will be omega x is 0, omega y will be 0, whereas omega z is equal to del v by del x minus del u by del y. These are the components of the vorticity vector, and we have only this term will exist, other two terms will contribute to 0. Now, what will happen to u? We have u is equal to nothing but phi x, that is equal to psi y. The psi is the phi is the velocity potential, psi is the stream function, and again we have v is equal to phi y, which is nothing but minus I x outside the tube. Then we have z, rather omega z is equal to del by del x. This is equal to del by del x, del v by del x minus del u by del y, and that gives us v is equal to minus I x. So, this is minus psi x x, then plus psi y y, because you put psi y. So, this will be minus of this, and if I put it in the Cartesian, this is in Cartesian coordinate, if I put it in the polar coordinate, this will give me del square psi by del r square plus 1 by r del psi by del r, and plus 1 by r square del square psi by del theta square. This is omega z. Now, let me talk about, because this is if I say let omega z is equal to a constant, that constant let me say 2k, let us say 2k within the cylinder, and this is because omega z is, if it is outside the cylinder, we have the flow is rotational. So, since outside the cylinder flow is rotational, so this will be 0, omega z will be, this will be 0. Now, if I assume that the flow is symmetric about origin, if it is symmetric about origin, once you assume the flow is symmetric about origin, what will happen? Del psi by del theta. So, that means psi becomes a function of psi r theta becomes psi of r, because theta component will not contribute to, So, in the process what will happen to this omega z? So, that means in the process from this equation, that omega z will be, if I look at this, then it will give me del square psi by del r square plus 1 by r del psi by del r, because this part is omega z, this is 2k, that will be within the cylinder, within the vertex, because the cylinder itself is the vertex tube, and this is 0 outside vertex, outside the vertex, because vertex is of radius, the cylinder is of radius, certain radius r is equal to a, if I say. So, then what will happen? This if I further simplify, that means within the vertex we have, then I can, so del square psi by del r square plus 1 by r del psi by del r can be written as 1 by r times del by del r del psi by del r, and this will be 2k within the vertex within the vertex, and this is 0 outside the vertex. Then, because there is a constant minus sign, that I choose as if it is k tilde, so I just without loss of generality I can take that minus sign again as a plus sign. So, then what will happen? If I simplify this, that within the vertex what will happen? I can easily get psi is equal to some constant c by r outside the vertex, because if I look at outside the vertex, what will happen, this will give me, it will give me c by r outside the vertex, here c is a constant. Now, sorry, this will give me del psi by del r, sorry, it will be del psi by del r will give me c by r outside the vertex, which gives me that psi is equal to c log r outside the vertex. Because this is very obvious, if you take this, this will be 1 by del r del psi by del r is 0. So, if you integrate with r, then you get some constant, r del psi by del r will be a constant. So, that means del psi by del r will be a constant times r, that is c by r, that is what c is equal to log r outside the vertex. Then what will happen to v, the component of velocity? V is nothing but del phi by del y, and this is nothing but del minus del psi by del x, or V can be written also in the r theta coordinate 1 by r del phi by del theta, which is nothing but minus del psi by del r, and I have been given psi is equal to c log r. So, that gives me my psi, rather V will give me 1 by r del phi by del theta, and that is minus c, psi is c log r. So, this will be minus del psi by r as minus c by r, and that gives me my del phi by del theta is minus c, which implies phi is equal to minus c theta. So, this is another result. Then if I look at, because phi is equal to, I have got outside the vertex psi is equal to c log r. So, if I put phi plus I psi, my W is nothing but phi plus I psi, that is phi is minus c theta plus I times psi is c log r. So, if I write it, I can also write it, if I take I times log r plus I c theta. So, that will give me I times log r e to the power I theta I times c is there, c I times, and that will give me I times c log z. So, my W becomes, this is the complex potential, that becomes I c log z. Now, if I look at by the definition of the strength of the vortex, what will be my k? If k is the circulation or k is the strength of the vortex, then k will be 0 to 2 pi, because q dot dr, and here I am looking at a circle. So, it will be giving 0 to 2 pi, that is minus 1 by r del phi by del theta r d theta, and that will give me 2 c theta, 2 c pi, because del phi by del theta, as I found my phi is minus c theta, because my phi is minus c theta, and once phi is minus c theta, this minus will be plus, r will get cancelled, del phi by del theta will give c. So, integral 0 to 2 pi to c pi. So, which implies my c will be k by 2 pi. When c is known as k by 2 pi, where k is the strength of the vortex, then my wz is equal to I k by 2 pi log of z. In fact, in many times we have started with this complex potential and proved that wz, if we have started with this and we have said that this represents a vortex of having strength k, and it is what we have derived by starting from the basic definition of a vorticity vector, from a basic definition of a rectilinear vortex of strength k. So, this is what we have obtained. So, what will happen if I change the, this is at z is equal to, if the vortex, if I say that if the vortex is at z is equal to z naught, and it is of the same strength k, then my wz will be I k by 2 pi to log z minus z naught. Now, what will happen if I have multiple vortex? Then the summation of the vortex will also, suppose I say that there are a finite number, large number of vertices. So, if I have n such vertices, then what will happen my w, and each of strength k, it can be easily seen that w is equal to I by 2 pi, or I will say each of strength k n. It can be easily seen that it will be I by 2 pi sigma, rather I will say j is equal to 1 to n, and the strength is k n. So, k j into log z minus z j, where the each of the vertex is at the point z is equal to z j. Now, with this, now let us look at a vertex pair. What happens in case of a vertex pair? A pair of vertices, it is nothing but a pair of vertices, each of strength k, but of opposite rotation. It is called a vertex pair. So, if I take w is, that means in this case w is equal to I k by 2 pi log z minus z 1 minus I k by 2 pi, because I said that they are of opposite rotation. So, the minus n comes log z minus z 2, and this can be written as I k by 2 pi log z minus z 1 by z minus z 2. So, if I just say that I have P is a point and this vertex is at minus a to 0, this is distance is r1 and this is r2, this is a to this point, this is a1, and let me call this a0. Both are of same strength k, then this point is a2. Okay, then this will be, this can be written as I k by 2 pi log, if this is called r 1 e to the power I theta 1 and this is called r 2 e to the power I theta 2, then this will give me I k by 2 pi log r 1 by r 2 plus I times theta 1 minus theta 2, and this is will give me which if this is w, then what will be my psi, which implies my psi will be k by 2 pi this part log r 1 by r 2. So, this is my psi, and once I say psi is equal to constant, that will give me the streamlines. So, if I say psi is equal to constant, that will give me r 1 by r 2 is equal to constant, and what is r 1 by r 2? That is nothing but, because the vertexity are position at x is equal to a 1 is minus a 2 a and a 2 is a comma 0. So, these are the 2 points. So, this will give me x minus x plus a square plus y square by x minus a square plus y square is equal to a constant, and that constant let me call it as b square. Say this b square is, this constant is nothing but b square I have taken. So, if I simplify this, then I can get it x square plus y square plus 2 a 1 plus b square by 1 minus b square into x plus a square is equal to 0. For each b, I can get a streamline, and how it will look like. If this is the axis, along this axis, then I will have so this will be like this. So, this is the way it will look like. These are the streamlines. In fact, these are circles. The streamlines will look like this. Now, if in the same way, I will talk about vertex doublet, like you have seen in case of a source, we have seen a doublet. So, there we used to say that two pair of sources, they are kept at a distance apart, so that if we multiply the strength of the source into the distance, and that should give us a constant. In the same spirit, we will define a vertex doublet. So, this is a vertex doublet. Unlike a source, we have a pair of vertex. Suppose I just say that consider a pair of vertex, one is of strength k, another is of strength minus k. The strength of minus k, this is plus k, and this is located at zero minus a 0, and this is suppose the point a 0. Then what will happen to the wz? This will be I k by 2 pi log z plus a, and this is gives me minus, because it is of opposite strength, minus I k by 2 pi, and this is log z minus a. If I look at this, this will give me, I will take minus I k by 2 pi. If I take this, then z plus a log z plus a, oh sorry, this is minus k, this is plus k. So, this is minus, this is plus. Okay. So, when this is minus, this is plus. So, I k by 2 pi minus I k by 2 pi log z plus a minus log z minus a. Then this can be simplified further, that I call it minus I k by 2 pi into, I can always write log z into 1 plus a by z minus log z 1 minus a by z, and this gives me minus I k by 2 pi, and this will give you, because log z first term will be log z, there is a minus log z, that will 0, and then you have log of 1 plus a by z, and that will give you a by z minus half a by z square plus 1 by 3 a by z cube minus and plus a by z plus half of a by z square plus 1 by 3, and this gives me some of the terms will get cancelled, and again if I put limit a tends to 0, I saw the distance becomes very close and k tends to large. K is such that a k limit a tends to 0 a k, because this value has to be, k will be, strength will be such that a tends to 0 limit a tends to 0, this will give me a finite value, k is large. So, if I do that, then my w z in the limiting sense to w z, and that will give me, because when a tends to 0, these terms will be contribute to 0, and then in the process this term, because k into a by pi, so that will give you some mu by z and minus n mu times I by z, and this is called the, so that means which implies w z is equal to minus I mu by z. This is the complex potential due to a vortex doublet. This is the complex potential due to a vortex doublet. Now, in the same way, we can call about what will happen if I have two more very nice example. We will talk about rows of vertices. This is very interesting. Often when a body is moves slowly in a liquid, when a body moves in a liquid slowly, then these rows of vertices plays a very significant role, and particularly what happens when a body moves, a rows of vertices are formed in the wake of the body, and in fact this is very common in many problems of marine hydrodynamics, this formation of vertices at the wake of the body. And so that in this context we will talk about the rows of vertices. For different types of different shape of the structure, there are different type of vertices which are formed on the in the wake of the body. Then let us see case 1. I will talk of a single vertices, single infinite row of vertices. Single infinite row of line vertices. Suppose I have a consider a case of a consider a single row of vertices, and the vertices are found at z is equal to, let me say this is the line, let me say this is z is equal to 0, z is equal to a minus a, 2a, 3a, 4a, like this, this side, and you have minus 2a, minus 3a, minus 4a. So, these are the points at which infinite row of vertices are formed, and each vertices, each of the vertex is of, each is of strength k. If each is of strength k, then what will happen to the sum? Let us take Wn, that means the first 2n plus 1 vertices. So, that will give me I k by each of strength 2a, strength k. So, I k by 2 pi log z plus log z minus a plus log z minus 2a. This side it will go up to log z minus a n, and similarly on the right side we will have log z plus a plus log z plus 2a, and it will go up to log z plus n a. This is minus n a, this is minus n a, this is plus n a. And if I look at this, what it will give me? That it will give me I k by 2 pi log z into z square minus a square into z square minus 4a square minus n square a square, and this will be, can be written as I k by 2 pi log of pi z by a. I am just multiplying a factor pi by a, and into, I can always rewrite this 1 minus z square by a square, because I am taking a square common, and a square, 4a square, I will take all this common, into 1 minus z square by 4 a square into z square minus a square, sorry, 1 minus z square by n square a square, plus some constant term will come. Plus a constant I can write, because this constant will come because of this one. Suppose I say I have a term pi by a, then I have a term log pi by a, here I will have a term a square, then 4 a square. All these things I can put it as a constant kn, as a constant. So, because these are constants, so without loss of, I can always adjust this constant and say that these constants are 0. Without loss of generality, I can assume these constants are 0, and in that case, when limit n tends to infinity, this w n, that will be called w, and in that case I will have I k by 2 pi, I have infinite series, product series log pi z by a, 1 minus z square by a square, z square by 4 a square into z square by n square a square dot dot dot, and this series is nothing but it is an interesting series, basically I k by 2 pi. This is basically the series of sin pi z by a. Pi z by a for infinite, this infinite series is nothing but sin pi z by a. It is a product formula of infinite series, and which gives me so this is my complex potential for the infinite rows of vertices. So this will give me dw by dz, which is nothing but minus u plus iv, and the right side will give me ik by 2 pi. This is into a by pi by a into this will give me cot pi z by a, and that is pi get cancelled. So it will be ik by 2 a cot pi z by a, and if I simplify further, which so if I separate it in terms of cosine and sine and expand it, my u I will get minus k by 2 a sine hyperbolic 2 pi y by a divided by cos hyperbolic 2 pi y by a minus cos 2 pi y by a 2 pi x by a, and my similarly my v will be given, I will get the my v will be k by 2 a into sine 2 pi x by a divided by cos hyperbolic 2 pi y by a minus cos 2 pi x by a. And again if I say as y tends to infinity, my u will be plus minus k by 2 a, where my v will be 0, and it can be easily seen that the negative sign will occur. It is a negative sign in the u for y greater than 0 and positive sign for y less than 0. So what will happen, that when y tends to infinity, there is a uniform. So y tends to infinity, that means away from the vortex, away from the infinite row of vortex, we have a fluid which is flowing at a uniform speed along the x axis, that is at a speed of k by minus k by 2 a and minus k by 2 a. So what physically it will represent, that the motion is like a, it is like a rigid block sliding over a layer of rollers. Separating. Then this is that the motion will look like rigid blocks sliding over a layer of rollers, separating them. Now, with this understanding, I will now go to, this is the case of a infinite row of vertices. Now, if I will go back to the column, that is, I will think of another vertex sheet, that is what is a famous vertex sheet, that is called von Karman vertex sheet. And in the case of a von Karman vertex sheet, we have two parallel rows of vertices, infinite rows of vertices. They are placed at the first one, it is placed at the points in a half of a b. So that means if this is the line 0, this is the x axis, it is on this side, and this is half by b, and this is, so this is along this line, and the other one is half of 2n plus 1 into a minus half b. So, these are the various location at which this vertex is. So, basically they do not lie on the same points, but distance apart from each other. So, similarly here, 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 like this. So, then if this is the case, then we can see if you look at the corresponding W and not spending much time, we proceed in the same way. If you look at the corresponding W, we will get I k by 2 pi log sin pi by a into z minus I b by 2, then minus I k by 2 pi log sin pi by a into z minus a minus I b by 2. And if you combine this, what will happen if I calculate d w by dz at z is equal to a minus I b by 2, then what I will get? I will get my u, I will get k by 2a tan hyperbolic pi b by a. In fact, I will here also what I will do in this case also I will proceed the same way, like I checked all the vertices, the sum of all the vertices at various points, and again the sum of all the vertices, and in the case of a here so here we have each of the vertices is the strength here is each of the vertices is of strength k. And if I add these two, that vertices are the points n a half b, that is, and both n is can be positive negative, n is plus minus 1 to plus minus 2 like this, then and I sum up them, then I get this and apply the product formula for the sine series, because I have a logarithmic term, then I will get these two sine functions, and then if I simplify this, then I will get this is k by, and again if I calculate it, what happened at z is equal to a minus b by 2, z minus I b by 2. So, then I will get this. Similarly, if I try with here other points also, then I can find at any point I can take up any vertices this, then also I will get the speed as the same, as the speed will remain the same. Similarly, if I consider the upper row of vertices and I can calculate the dw by dz at any point, I will also find that the speed will remain the same. That means, the speed will be unaltered by due to the. So, it will be unaltered wherever I consider the speed remains same. That means, the vertex configuration is unaltered with time for all time t, and once this is, and this vertex configuration is often called, this is often realized, this kind of when a flat plate moves through a liquid broadside through a liquid. This kind of vortex is realized when a flat plate moves through a liquid, and this is the well known vortex, von Karman vortex heat. And in fact, this vortex theory, like while talking the motion of a ship in the water or any other body in the water, always at the wake we find the formation of vortex, and this vortex it is very one can observe them and sometimes also we see there are a lot of emphasis is given on the vortex heading, particularly it is basically major emphasis is given when a body is moving in a fluid, basically on the there are two aspects there, the importance is given, flow separation and vortex heading, and so that those details will come in a specialized course. I will not go to those details here in the context of this course are in the context of this lecture, but with this background on vortex motion I will stop here today. Thank you.